we will discuss about electric field due to infinite sheet of charge. Okay, so let us consider some infinite sheet of charge as shown here. Okay, and this is having a charge density which is given as rho s. Okay, the charge density is rho s. Charge density which is given as rho s. Now let us first consider the coordinate system for this. So we have the z axis, then we have the x axis, then we have the y axis. Okay, so this is x, this is y, and this is z. Okay, now let us consider a small differential area which is given as ds, a small differential area ds. So differential area which is given as ds. Okay, now we will consider the charge in this area, the charge in this differential area which is given as dq. So charge in this differential area is given as dq, and due to this charge you can expect some electric field at some point which is at height h from in the z axis. It is height h in the origin. So consider that this sheet of charge is placed in xy plane. Okay, this sheet of charge is placed in xy plane. So this is at some distance h. Okay, so at this point you can experience some electric field anyway. So you can see here, this will be the electric field. Okay, electric field like this. Okay, so you can experience some electric field like this, and due to the small charge you can have the electric field which is dE. Okay, now we will first define what are our points. Our points are actually this point and another one. Okay, so my point in the xy plane can be defined using rho, phi, and it is in the xy plane, so z equal to 0. So what is my rho? This is in the cylindrical coordinate system, this is my radial distance, and this is phi. Okay, this is the radial distance in the xy plane, and the point in the z axis, point on the z axis can be represented as, my rho will be equal to 0. I can have some phi which is in the same direction for the point in the xy plane, and I can have something like this is, yeah, this is h. Okay, so the vector which is joining from these 2 points is like this, because this is the direction of the electric field, and the vector which is joining these 2 points can be represented as r bar. Okay, so this is my vector. I can say this is my vector. My vector is given as r bar. Okay, so what is my r bar? My r bar is equal to my final point. You see, this is my final point 0, and here it is rho. So 0 minus rho into a rho plus phi minus phi into a phi plus h minus 0 into a z. So I will get my r bar as minus rho into a rho plus h into a z. So this is my vector. And what will be the magnitude of this vector? The magnitude of r bar is given as root of, or I can say it will be represented as minus rho square plus h square whole power 1 by 2, but minus rho square will be equal to, minus rho square will be equal to rho square. So I can represent my r bar, I will represent my r bar, I will write r bar again, rho into a rho plus h into a z, and the magnitude of r bar is equal to rho square plus h square. Okay, now if I want to find the cube of it, rho square plus h square whole power 3 by 2. Okay, now why I am taking the cube? Because it appears in the equation for the electric field. Now I am going to write the equation for the electric field dE, which is equal to 1 by 4 pi epsilon 0, and what is the charge? dQ is the charge, then it will be dq into rho square, sorry, not rho square, r bar by magnitude of r bar, okay, magnitude of r bar. So this will be equal to r bar by magnitude of r bar the whole cube. So this will be equal to 1 by 4 pi epsilon 0 into dq into r bar is equal to minus rho into a rho plus h into az divided by rho square plus h square whole power 3 by 2. Now what is my dq, because I have no idea regarding the term dq, okay. So what is my dq? dq is equal to, you know, this is my sheet of charge. The sheet of charge is having the charge density, that means the charge per unit area, it is given as rho s. So if I know this rho s, if I want to find this, the charge dq in the small area, ds, how to find it? Just multiply this rho s with the ds, okay. Now what is this ds? This is my dq. Now what is my ds? This is the question. You see, we are using the cylindrical coordinates. So in the cylindrical coordinate system, you see here this is my x and this is my y and this is my z, and this is my small differential angle. My differential angle is d phi, okay. This will create a small arc. This is my small arc which is created by the differential angle, and the change in the length, is given as d rho, because this is up to the, for this point, particular point here rho, this is d rho. So what will be my arc? You know that angle is equal to arc over radius. So I can write my arc, I can write the equation for arc as angle multiplied with the radius. And what is the differential angle? Because change in the angle is d phi. So d phi into the radius. What is the radius? The radius is given as rho. So this is my small arc. If I want to find the small area due to this small arc, if I want to find the small area here, my area ds will be equal to, you see, this is the small arc and you have the change in this d rho. So I have a small area here. So the small area is equal to d rho into this arc. So d rho multiplied with arc. What is my arc? Arc is equal to d phi into rho. So I can write my equation for ds as rho into d rho into d phi. So I got everything in terms of rho. Now I can find my equation for dE, which is equal to 1 by 4 pi epsilon 0, 1 by 4 pi epsilon 0 into dq. What is my dq? It is rho s. dq is equal to rho s into ds. So it is rho s into ds, then rho s into ds, then I have the terms minus rho into a rho plus h into az divided by rho square plus h square whole power 3 by 2, okay. But I can substitute my ds with this equation. So my dE will be equal to 1 by 4 pi epsilon 0, then I have rho s, okay. Then ds will be substituted with rho into d rho into d phi, okay. So I will write this rho d rho into d phi or d phi into d rho at the end, so that it will be very convenient, minus rho into a rho plus h into az divided by rho square plus h square whole power 3 by 2. So this is my dE, this is my equation for dE. But if you carefully see the scenario, if you have this is x, y, z, then this is your sheet of charge. If you consider a piece here, a differential element, a differential area, you can have the same thing in the diagonally opposite also, okay. So what will happen? this will create some electric field along this direction. Similarly, this will create some electric field along this direction. So electric field is created along this direction and this direction. Now, if there are two things coming, that means I will redraw it again. One is coming like this, another is coming like this, and this is your z axis, that means ZZ. Now you see this is coming like this, okay, and this is coming like this. Now you can resolve this into two components. What are the two components? First of all, you can have two components. One is in this direction, which is a rho, and another is in minus a rho, and this is another one is az. Now if you are resolving this vector, which is, let's say this is 1 and another one is 2, if you are resolving this 1, what will happen? You will get a component in this direction, in the direction of arrow, and you will, from the 2, which is diagonally opposite component, that means, which is this is the piece number 1 and this, let's say this is the piece number 2. So from the small differential piece, you will get two components. So one will be in the direction of arrow and another will be in the direction of minus arrow. What will happen? These two components will cancel. This component cancel. So what will happen? Only one component will be remaining. What is that? It will be the az. So in this equation, in the above equation, you see that this component, which is the component of arrow, this will cancel out. So this component will cancel out, okay. So we have only, so we don't need to do the integration and find the solution. So if we can, if we want to simplify the integration, we can write the equation like this. This is equal to rho s into rho by 4 pi epsilon 0. Then I will remove the component in the direction of arrow, then it become h into az, okay. Then d phi d rho, d phi d rho, then divided by rho square plus h square whole power 3 by 2. Now we want to find the total electric field. If we want to find the total electric field, which is E, we have to integrate over the whole surface, which is dE. So we are doing the integration of this. So it is rho s into rho divided by 4 pi epsilon 0 into h into az. I will write it at the end. So this is my az. Then I have d phi and d rho. I will write d rho first, d rho and d phi, and this will be rho square plus h square whole power 3 by 2. Now you can see that if we want to integrate over the whole surface, we have two variables, one is rho and another one is phi. So we have to do the double integration. That means we have to integrate from rho along rho, and we also want to integrate along phi. So what will be the situation here? This is z, this is x, this is y, and we are here, we have the differential element here, and you know that this is the phi. So phi is changing from 0 to the whole circle, that means 2 pi. So phi is changing from 0 to 2 pi. And what about the rho? Rho is this radial distance. Since my sheet is something like this, which is infinite sheet, you see that my rho is changing from rho equal to 0 to, it is changing from rho equal to 0 to, it's a large sheet, so it is like rho equal to 0 to rho equal to infinity. So rho is changing from 0 to infinity. If I consider like this, I will get the whole sheet. So I hope this part is clear to you. So I will rewrite everything in the next page. So my electric field will be equal to integral from 0 to infinity, and phi changes from 0 to 2 pi, okay. Then I have rho s into rho s into rho by 4 pi epsilon 0, then h, then I have d rho d phi d rho d phi, then Az, then divided by rho square plus h square whole power 1 by 2, right? Sorry, not 1 by 2, it's whole power 3 by 2. Okay. Now we are integrating with respect to phi. We are first integrating with respect to phi. So what is the integral of d phi? Integral of d phi is equal to phi. So electric field become integral rho changes from 0 to infinity, then rho s into h divided by 4 pi epsilon 0, then integral of d phi is phi, and phi changes from 0 to 2 pi. Okay, then I have remaining d rho and Az, and also rho square plus h square whole power 3 by 2. So if I put the limit, you see here phi is equal to 2 pi and 0. So 2 pi minus 0, it will be equal to 2 pi. So I will substitute this. So this become integral rho is equal to 0. I will change the color. So this become rho equal to 0 to infinity rho s into h divided by 4 pi epsilon 0 into rho square plus h square whole power 3 by 2, then into 2 pi will come here, then d rho into Az. So 2 pi and the 4 pi, this will cancel and it will change to 2. Okay. So what will happen here? You see, this will change to 2. Now we will get my electric field as integral rho equal to 0 to infinity rho s into h divided by 2 epsilon 0. Then you have d rho into Az divided by rho square plus h square whole power 3 by 2. Now you see here that there are variables like rho, d rho and also rho square. So we will use a trick which is a rule in integration. We can, by using the substitution of variable, we will put rho square is equal to u. So this implies that 2 times rho into d rho, that means if you differentiate on both sides, you will get this as du, or we can get rho into d rho will be equal to du by 2. So we can substitute this rho into d rho as du by 2, and we can substitute rho square as u. Now when rho is equal to 0, the u will be equal to 0, and when rho equal to infinity, then what will be u? U is equal to rho square. So infinity square, again infinity. So we are going to rewrite it. So electric field will be equal to integrate. I am going to change the variables. U changes from 0 to infinity, then rho s into h divided by 2 epsilon 0. Then I substitute the variables. You see rho into d rho, I will substitute with du by 2. So this become du by 2, then rho square is u plus h square whole power 3 by 2. Now I can write this as electric field is equal to u equal to 0 to infinity. I forgot the direction Az. Okay, so Az also this is there. So rho s into h. Okay, then 2 into 2 become 4. Okay, 4 epsilon 0, then u plus h whole power minus 3 by 2. I can write like this. Okay, into du, then Az. Okay, so electric field will be equal to, you know that integral of x plus a whole power n dx will be equal to x plus a whole power n plus 1 divided by n plus 1. So I will use this rule here. Okay, so this will be equal to rho s into h divided by 4 epsilon 0, then this become u plus h whole power minus 3 by 2 plus 1 divided by minus 3 by 2 plus 1. Okay, this will be the integral, then into Az. Now I have to put the limit. My limit is like u changes from 0 to infinity. So my electric field is equal to, when I put, so my electric field will be equal to rho s into h divided by 4 into epsilon 0. Then this become u plus h whole power minus 1 by 2. Okay. Then this become minus 1 by 2. So you can see here a lot of things will cancel. This will cancel. So you will get it as 2. Okay. So you will get this as rho s into h divided by 2, and there is a negative sign. Then this become u plus h whole power 1, u plus not h, I think h square, sorry for this, u plus h square. So u plus h square, that means whole power minus 1 by 2 means u plus h square whole power 1 by 2. Okay. Then I will put the limit, then I have the direction, I forgot to write the direction. So then I have a direction Az, and u is changing from 0 to infinity. Now this will be equal to, okay, I will use the next page. So electric field, I will rewrite the equation. Electric field is equal to minus rho s into h divided by 2, okay, then divided by 2 into u plus h square whole power 1 by 2, okay, whole power 1 by 2. Then and we have to put the limit 0 to u is equal to 0 to infinity into Az. So the electric field will be equal to, I will put infinity, then if I put u equal to infinity, then there will be a term 1 by infinity. 1 by infinity will be equal to 0, then minus, then you will write minus rho s into h divided by 2. Okay. Did I miss anything? Did I miss anything? Yes, I missed epsilon 0. So epsilon 0. So epsilon 0. Then I will put u is equal to infinity. Sorry, when I put u equal to 0, this become 1 by u equal to 0, 0 plus h square whole power 1 by 2 into Az. So the electric field become minus of minus, this become plus. So rho s into h divided by 2 epsilon 0 into 1 by, this is h square, that means whole power 1 by 2 means root of h square, this into Az. This is equal to rho s into h divided by 2 into epsilon 0 into 1 by h into Az. So you can see here these terms will cancel. So my electric field will be rho s divided by 2 epsilon 0 into Az. So I hope this part is clear to you. So in general I can write, if there is a sheet of charge like this, and this is the normal to the plane AN, then my electric field will be normal to that plane. That means the electric field will be equal to rho s by 2 epsilon 0 into normal to that plane. So this is the general equation. Okay, this is the general equation. So this will be the normal, which is AN. Okay, so you see here that since we have this z, x and y, and this is my sheet of charge, the electric field due to the sheet of charge at distance h is given by, the electric field is given by rho s by 2 epsilon 0 into Az, because normal to this particular configuration, which is the sheet of charge is placed in xy plane, is Az. But you can see that this is independent of the distance h. So it is independent of the distance, it is independent of the distance. So this is very, very important conclusion. Okay, so I hope this is clear to you. Okay, thank you.